Right, so today's lesson is on special segments in triangles. There's 4 different kinds of special segments that we can draw in a triangle. Let's look at the first one. The first one is called a perpendicular bisector. So let's take that name and think about what it means, okay, before we come up with a definition, because I bet we can come up with a pretty good one just by analyzing this name. Perpendicular means, if you'll remember, 2 lines that make a right angle to each other. And we usually indicate it with like an upside down T and a box there to show that that is a 90-degree angle. And then bisect, do you remember what that means? We talked about that way back in chapter 1. To bisect something means to cut it in half. So if we have a perpendicular bisector, my thought is that we're going to have a line that's going to bisect another line, and it's going to be perpendicular to it. So it's going to cut it in half. So something like this up here, where these 2 segments on either side of that perpendicular line are congruent to each other, so that the entire segment is bisected or cut in half. So formally, we would say the definition like this: a line or line segment that passes through the midpoint. Remember, midpoint is the point in the middle. So up here on our picture, it'd be right there, of a side of a triangle and is perpendicular to that side of the triangle. So we would just need to make a triangle out of this. And there we have our perpendicular bisector in that triangle. Okay, so a little bit neater drawing would look like this. And the triangle could be any kind of triangle. Okay, so here we have a perpendicular line XY to side AB. Now, how do we know that it's perpendicular? Remember, our little box tells us here. Or if we had a 90 written in here, that would tell us. How do we know that it's a bisector? If we look at side AB, we can see that YB is congruent to YA, meaning that that entire side is cut in half, which is the definition of a bisector. So XY is a perpendicular bisector of side AB. So we're looking for markings here so that we can determine the relationship. Okay, so know what a perpendicular bisector is. Be able to recognize one with the different markings. Be able to draw one including these markings. Now there's a theorem or 2 that go along with this idea. The first theorem says that if there's a point on this perpendicular bisector, it is going to be equidistant. Word from the past, what does that mean? Equi means equal, distant means distant. So it has the same distance or equal distance from the endpoints of the segment. So here's my segment AB. I have my perpendicular bisector XY just like I did in the previous screen. So any point that is on this segment XY will be the same distance from point A as it is from point B. As you can see here in our labeling, segment XA is 10, so therefore XB has to be 10. They're equidistant. Okay, so I could put another one up here, and I could draw a line to A. I could draw a line to B, and if I told you that this line segment is 16, what is this one? You would say 16. Okay, so they're going to be the same. So we can set them equal to each other. The opposite of this theorem is true as well. Any point that is equidistant from endpoints of a segment is going to lie on the perpendicular bisector. Okay, so here we go. CD is a perpendicular bisector of AB So give me an equality statement. What two distances are we going to know will be congruent or equal to each other? Here we have point X on this perpendicular bisector. What we just learned is it is equidistant from the end point. There's my two endpoints. So this segment AX is congruent to segment BX. So their distances will be the same. They will be equal to each other. So AX, distance, remember if there's no line segment or any marking over it, it means the distance or the measurement of AX is equal to XB. Let's do an example where we have to work it out. So here is our triangle ABC, and we have drawn three perpendicular bisectors, N, M, and R. And these figures get real crazy. Lots of lines drawn in, lots of markings. So just don't get overwhelmed. Just take a step back and look at individual parts instead of the whole thing, because it does get overwhelming sometimes. So these boxes here tell us that segment R, line segment N, and line segment M are perpendicular bisectors because we see these perpendicular 90-degree angle marks. Okay, so that means that this point D is on all three of those perpendicular bisectors. Therefore, it is equidistant from all of these endpoints A, B, and C. Now let's see what information we were given down below. If BD, so BD right here, is 3x plus 4, AD is 6y plus 1, and CD is 19. Find x and y. Well, there's no way I can find x or y by using these two phrases that have the x and the y in it at the same time. I can't put them in the same equation and solve for either one of them. So that makes me think that I'm going to use this 19. Okay, so CD, how is that 19 related to, let's do this first one, BD. How is CD related to BD? Well, because this point D lies on the perpendicular bisector, these two distances to the endpoints are the same. So I can set them equal to each other. I can say 3x plus 4 equals 19. And then I just do that algebra. 3x equals 15, x equals 5. So that takes care of the x. Now let's look at the y phrase. What segment is that correlating to? It's correlating to AD here. So now I have to ask myself, how is AD related to this 19 CD? Or is it? Well, again, point D is going to lie on both of these perpendicular bisectors. It lies on R. So it is equidistant from the endpoints here, A and C. Notice these congruency marks here show us that it's a bisector. So again, those two segments can be set equal to each other. So AD is 6y plus 1. So I'm going to write that down. And that's going to equal 19. So 6y equals 18 if I subtract the 1 from both sides. And then divide by 6, y equals 3. So my two answers are x equals 5, y equals 3. Okay, so by knowing that those parts are congruent, I can set them equal to each other and solve. Our second segment in triangles is the median. Think of the median in the street, or even when you were in junior high and you learned about mean, median, and mode. What was the median? When you hear that word, it usually means middle. So in a triangle, a median is a segment that connects a vertex. Remember what a vertex is. It's one of these corners of your triangle. It connects a vertex of a triangle to the midpoint, the middle of the opposite side. So you've got to go all the way across. We're going to start at this vertex and go all the way across till we hit that middle point of that opposite side. I know it's the middle because I see these congruency marks. Notice it is not necessarily perpendicular. It could be, but it doesn't have to be. So in this example, BZ is a median. So as we go through these, you're going to be expected to be able to recognize a drawing as a median or a perpendicular bisector or an angle bisector. Okay, these four segments that we talk about, you need to be able to recognize them in a drawing based on these markings. So you have to know these definitions. What does it start? Where does it start and where does it go? And what marking should I expect to see? So here's an example of how we might use this to solve a problem. We're asked to find x. Okay, well, both of my phrases here have x in them. So I could put them in the same equation. That's a possibility. So if BD is a median, notice these congruency marks here. Anytime parts are congruent, we do what? Set them equal to each other. So CD, we can set equal to DA. So that's all we need to do is take these two phrases and set them equal to each other. And then it's just a good old algebra problem. I'm going to get my x's on the left because I like to have positive x's. So my 7x cancels out. And then I have to move my whole numbers over to the other side. Can't have it all on one side equal to 0. I'll divide by 6, and my x equals 4. Now I could go on to say find the length of CD, in which case we would need to plug it in. Or find the length of DA. We could plug it in. If we did that, what do we expect to see? We should get the same answer both times. If these are truly congruent, then we would get the same answer. Okay, on to our third special segment. It's called an altitude. When you think of a plane, an airplane flying at a certain altitude, what does that mean? Most people think of it as the height of the airplane. And then my next question is it the height like from 5 miles away from us on the ground, or is it the height straight down to the ground? And most people tell me that it's the height straight down. So if here's the earth and we have this airplane, the altitude is going straight down. Okay, that means it's going to hit at a right angle. So the definition of altitude is a segment drawn from the vertex of a triangle perpendicular to the opposite side. So here is our triangle. We can pick any vertex, and if we go straight down, again, we need to see this perpendicular box there to know that it's an altitude. It goes straight down. Okay, perpendicular bisector, remember, started in the middle and went straight up. It did not necessarily go through the vertex. So those are some different things you're going to look for. If it starts at the vertex, goes straight down, and we don't know that these are perpendicular, or are congruent on either side, that's an altitude. But if it hits in the middle and we see those congruency marks, then we know it is a perpendicular bisector. Okay, so let me clear that off so that's not confusing. So in this picture, we can say BX is an altitude. We can draw more than one altitude. Okay, and sometimes the altitude might hit outside of the triangle, depending on the type of angle, in which case we would need to extend this kind of mentally. If I can get we just kind of mentally extend that side, and then we drop a perpendicular line to it, then that would be our altitude on that side. Okay, we can drop an altitude on this side. It's hard to draw with this pad. Okay, so in this situation, the one that we've drawn, Bx, is an altitude. But that brings me to a point I want you to understand, is that all of these segments that we are drawing, we can draw 3 of them in any given triangle. Because we have 3 sides and 3 vertices, we can draw an altitude from any vertex. We can draw a perpendicular bisector from any side. And we'll get to that in the next lesson. But just keep that in the back of your mind, that there's 3 of them in any triangle. So here's an example. It says find x and the measure of angle 1 if EG is an altitude. Okay, so I have to think, what does that mean to be an altitude? That means it's coming in at a 90-degree angle here. Okay, it might not be drawn in, but the fact that it called it an altitude tells you that that's a 90-degree angle. So I know now that angle 1 and 2 together make 90 degrees. Well, look, they gave me a representation of both angle 1 and angle 2. Am I going to set them equal to each other? Do I know? Do I have any congruency marks there telling me that they're the same? No. Okay, don't automatically assume just because 2 things have an x in them, you're going to set them equal to each other. You have to ask yourself, what is their relationship? If you can't say that they're congruent, then you are not going to set them equal to each other. In this case, I know that they both make a 90-degree angle, so I'm going to set them. I'm going to add them together and set them equal to 90 degrees. So there's my angle 1. I'm going to add that to angle 2. And together they make 90 degrees. So it's all about understanding the relationships. Okay, I'm going to put my x terms together. I put my whole number terms together. Now I subtract my 18. Let's continue over here. 9x equals 72. If I divide by 9, then x equals 8. And again, because I was only asked to find x, I'm finished. But I could also plug it in here and find, let's find the measure of angle 2. If x is 8, then I'm going to replace the x with the 8. So 24 plus 2 is 26. Whoops, 26. Now, how would I find angle 1? There's actually 2 different ways I could do that. I could plug my 8 in for x up here in my angle 1 measurement here. Or because I know together they make 90 degrees, I could just say 90 minus 26. Okay? It doesn't matter. Both relationships are true, mathematically sound relationships, so go with the way that makes sense to you. Okay, our 4th segment is called an angle bisector. Based on what you know about those 2 words, what do you think an angle bisector does? Hopefully you said that it divides the angle into 2 equal parts, cuts it in half. It's a ray because it has to start at the vertex. It actually has an ending point. Okay, so it starts at the vertex of an angle and divides that angle into 2 equal parts. So it would look something like this. Now remember, we are doing this in triangles, so we could close this so it would look like that. And again, we could draw 3 different ones, one from each vertex. Okay, so any given triangle could have 3 different angle bisectors. Oops. Okay, notice the congruency marks. That tells us that it divided it into 2 equal parts. So if I know one part, I know the other part. I can set them equal to each other. A theorem that goes along with this definition says that any point on the bisector of an angle is equidistant. There's that word again. The same distance from the sides of the triangle. So if we have this situation, anywhere I put this point, does not matter where I put it, I could put a point here, it's going to be the same distance from the bottom side as it is from the top side. Let's do 2 congruency marks there. So again, by knowing these relationships, I can find missing parts. So these 2 segments could be set equal to each other. These 2 segments could be set equal to each other as well. And then the opposite is true. Any point that's equidistant from the side of an angle is going to be on an angle bisector. So we're saying the same thing just backwards. So because I know that these 2 segments, let's call this point, if I can get my pen to work, let's call this point M. So if YM is congruent to XM, then I know that M is on an angle bisector. So I can now say, yes, BZ is an angle bisector. So let's do some problems using these ideas. If we know that ED is an angle bisector of an angle ACD right here, let's mark it, is 10A minus 2. BCD, let's mark it right here, is 6A plus 22. Find A. All right, well, they're both A's, so I can put them in the same equation. The question is, am I going to set them equal to each other, or are they going to add up to something else? Well, because these different angles are marked congruent, then that allows me to set them equal to each other. So here's our equation. 6A plus 22 equals 10A minus 2. Now it's just an algebra problem. I move my A's to the same side, cancel here, bring down the 22. I get 4A. Now I've got to move the 2. I don't want everything on the same side. That would make it set equal to 0. We don't want to do that. Those cancel, and then if I divide by 4, I get A equals 6. Again, that answers the question, but if it asked me to find the measurement of either one of these angles, I'd have to go plug it in. And I could plug it in either place. Would I need to do both? No, because they're congruent. Once I find one, I should know the other. Here's another.